welcome back. So today we're working on chapter 10, the structure and formation of stars. If you recall, last time in chapter 9, we really took a look at many physical properties of the stars and created this family of stars, things like their diameters, the distances. Luminosity was a new term for us, absolute visual magnitude, another one. Looking at density and their masses. So many physical characteristics that really the Hertzsprung-Russell diagram helped us to separate many of those: temperature, luminosity, and a spectral class for our family of stars. Now we want to look at chapter 10. That's going to show us what's going on internally with our stars, how stars are born, and that sort of thing, and their lives on the main sequence. That's where they spend the majority of their time. So chapter 10, the what are we summary for chapter 10 is we are myth makers and explainers. So we try to make up stories. I think of the constellations and how many stories are in the constellations, the Greeks and the Romans and the Native Americans. They love to make up stories to try to explain constellations, and that's just one example. But we do try to explain nature, our surroundings, and so science is just a natural extension of our need to explain, the explainers. And so a lot of science is going to go into chapter 10 here, and they do show you some of the evidence of how we know anything about our stars. We can't go visit them, we can't set foot on them. So how do we know, kind of thing? And science helps us with that. So we do want to take a look here at this structure here. And so stars are not eternal. They have a beginning, and they live their lives, and then they do die in a variety of ways, which will be chapter 11, where we discuss that. But their lives are pretty long in comparison to our human lifetime experiences. And so the stars we look at tonight are the same stars that our grandparents and great-grandparents and great-great-grandparents have looked out upon as well. So they don't change in a human lifetime. So they are born and they do die. They're not eternal. So how can we know about those internal processes I was talking about when we can't see inside of them and we can't live long enough, right, to see them evolve? And so the methods of science are what we're going to be using to kind of explain this. So stars are very simple. They are very elegant, very powerful sources that are balanced. There's this one key word of balance for a star. It's got to balance the inward pull of gravity, trying to make it collapse, with this sort of outward pressure that the higher temperature and the higher density at the internal part of the star is creating. This outward pressure balancing the inward pull of gravity. So balance is something that we can consider in the internal structure of our star. So, and they do mention here that it is important that we use our imagination here and think about stars as if they have concentric shells or layers to them, and that you can have different things occurring in different shells within your star. So the core could have something going on with it, an outer layer outside the core could have something different happening, and so forth as you went out towards the surface of the star. So different things can happen with each of those layers, and so it's going to be good to try to imagine those layers, even though stars don't have any separate layers, but things can happen within each layer that are different. So we do have some laws that these stellar laws that they talk about. And so we want to take a look. This will be table 10.1 in your books, and they'll, at the end of it, have it in the PowerPoint as well. But There's two here. The first one is the law of conservation of mass. Okay, these conservation laws. So conservation of mass is our first one. Okay, and so this is kind of the thing that, you know, matter's neither created nor destroyed sort of thing. But that amount of mass, the total mass of your star, has to equal the individual masses of those layers. And so it is important to think of the star with those layers. So similar to like the weight of a cake, if you had a layer cake, they're saying here, the whole weight of that cake must equal the sum of the weight of the layers. So we can use that little analogy with our stars as well. So the sum total mass of your star has to equal each of those little layers within it. Okay, conservation of mass is that one. Your second one, conservation of energy. Okay, so this one is saying that a star must be equal, so the amount of energy flowing out of your star or out of a layer within your star must equal the amount of energy coming in. So input and output must balance, and that's within each layer within your star. So conservation of energy. Okay, total number of energy leaving the surface. Okay, which is its luminosity. If you recall that luminosity, the amount of total electromagnetic radiation output of your star must equal the sum of the energies that are being generated within each layer of your star. So energy being generated, so that balance going on. Inward pull of gravity being balanced by that outward pressure from generation of energy that's happening. So conservation of mass, conservation of energy, so these must be in balance. Okay, those first two. The third one here, the hydrostatic equilibrium. Okay, so for this one, the weight of each layer, okay, must be balanced by the pressure of gas, okay, that causes this outward push, pressure, we call that. They must be in balance. So conventionally, if we think of maybe a pyramid they're talking about, so the people on the top row don't have anybody to hold up. So their little pressure balance is not going to be as great. The ones, so the outer layer of the star in that analogy. But the people down on the next row of your pyramid, they've got to balance the weight of the people above them on the top row, so they've got to exert a little more pressure to achieve that. So in a stable star, those deep layers have to support the weight of all those layers above it. And so, of course, it's gaseous all the way through, so the weight pressing down on a layer must be balanced by the gas pressure in that layer. And if it becomes too high or too low, some things can happen. If your pressure's too low, the weight from above is going to start to compress in on it, okay? Then if the pressure becomes too high, it's going to expand and lift those layers. And so there is this nice hydrostatic equilibrium, pressure balancing weight, that is occurring within your star with the generation of energy and then kind of trying to balance gravity, that inward pull of gravity. So balance definitely is occurring between these delicate little balance going on. And there's a nice little picture here. So you may not be able to see the coloration very well, but the size of the arrows you should be able to see. The darker maroon color is pressure, and then these orangey colors are weight from gravity pressing in. So as you can imagine, the arrows are wider here in diameter, meaning a higher pressure or a higher weight down towards the center, as you can imagine, because it has all of these layers within the star to support got all this weight pressing down on it from all those layers above. So its pressure at the center has to be greater. So the higher temperature, the higher density is going to create that outward push that's trying to balance the inward pull of gravity. And so each layer, you can see how the arrows are getting a little smaller, so the farther out you go towards the surface here of your star, this little hydrostatic equilibrium that pressure doesn't have to be so great because the weight of gravity isn't that large pulling in on it, trying to compress it in. So there's this nice balance going on all the way through. So the pressure in each layer is going to grow larger as you get towards the center because more and more pressure, more and more weight, we've got to keep that balance happening. So that's sort of the hydrostatic equilibrium, and of course that pressure, that outward pressure has to be dependent upon that inward pull there. So temperature and density are key to what's happening with the pressure in your gas. Okay, so greater the inward pull of gravity, the greater your pressure is going to have to be. And they kind of work hand in hand for that internal kind of structure in there, because the more it compresses in because of gravity, that's going to increase your density. The molecules are going to get closer and closer together, and they're going to collide more, and that's going to increase your temperature. Okay, and so that's going to create the pressure, the outward pressure, and so there's a nice delicate balance that's going on with the hydrostatic equilibrium. Okay, so it can inform you of some things in the inner structure of the stars, but we need one more law to complete our description of our star, and that is the flow of the energy from inside to outside of the star. And so that's going to be our energy transport law. Okay, and basically the law is saying that the energy is going to flow from regions where it's very, very hot to regions where it's cooler, and so working its way essentially from the interior of the star out towards the surface of the star where it would be cooler. So that's sort of the direction, always from higher to lower, kind of a gradient of energy transport. And there's three means of energy transport that they mention here: conduction, convection, and radiation. Really just two of these are important in our stars, energy transport. But conduction, we're probably familiar with conduction. It requires sort of atom to atom contact, direct contact. So something like this spoon, this metal spoon over a flame, you're heating up your metal spoon. Well, metal conducts heat very well, and so that energy is flowing atom to atom within that metal, and eventually your hand would get really hot and you drop that spoon because there is conduction happening. It's moving its way atom to atom, and so that's conduction. Now, conduction is not important in star energy transport because those atoms are, gaseous form, and they're really buzzing around. They're not in close contact, so stars don't have a high enough density for that conduction to be important. So that's not going to be important with our stars anyway. But another way is through radiation. So here we've got radiation out in all kind of directions. If we were to put our hand around that candle, we would feel kind of the flame, the heat of energy being kind of infrared heat energy there being radiated. So radiation is your, like I mentioned, there's several layers to a star, so different things can be happening in different layers. And so towards the internal part, so in the interiors of most stars, the energy transport is through radiation out in all directions and emitted in different directions as it's working its way from the hot interior out towards the cooler surface. So radiation, especially towards the internal part, is your main way of energy transport. And here they're talking about, how well that radiation is going to flow. They talk about the opacity of the gas is sort of its resistance to flow of the radiation. Certainly a hotter gas is going to be more transparent so that the flow will go much easier than a cooler gas. So a cooler gas would be more opaque, or this opacity that they're talking about. Hotter gas being more transparent than a cool gas. So if it becomes too opaque or opacity is high, radiation can't flow through that, and so it gets blocked, kind of like a dam blocking water. But eventually, when you get enough heat built up, enough pressure behind it, and the gas kind of begins to churn, and then we do set up, this next flow called convection. And we looked at convection when we looked at our star, the sun, at its surface region, where you start to get this churning happening. The hot gas is going to rise upward, out to where it's a little cooler, cools off, and then the cooler gas sinks back down. And so you set up a convection cell. That is what was causing the granulation appearance on the surface or the photosphere of our star, the sun. So this is like the third means of transportation of energy. It's called convection, sort of that convection cell. And so if you do recall that, now look at this little picture if you can see it. This interior part of the star, is a radiative zone. So radiation is the means of transport. But right out here where you're seeing the little convective cells, the hot gas rising, the cooler gas sinking. So they're using the red color for rising hot, and this bluish color for cooler sinking kind of thing there. But a convection cell happening, in there, a little cross section of it. This is occurring towards the outer part, the outer layers of your star. So two different means of energy transport occurring. And like I mentioned, different things can be happening in the different layers within a star. So more towards the center, we've got the radiative zone, and the outer part, we have a convective zone. So different means of energy transport together with the flow. So those are known as the 4 laws of stellar structure. And this is going to help us to understand how stars are born, how they live their lives, and how they die. So conservation of mass, the sum, the total equals all the sum of each layer of masses. Total luminosity, the sum of energy generated in all your layers. Again, different layers. Hydrostatic equilibrium, weight on each layer, balanced by the pressure within that layer. So the more layers you've got on you, the greater your pressure has to be. So those internal parts of the star have to create a lot of pressure to balance that weight. So that's hydrostatic equilibrium, that pressure stemming from the temperature and the density of the inner layers there. Energy moves from hot to cool, that's our gradient, hot to cool, either by conduction, radiation, or convection. So that's the energy transport laws. And remember, conduction is not important in our stars, our normal stars anyway. So radiation and convection would be the main ones there. So that's that. And I know that says table 7.1, but we are in chapter 10, so this is an old PowerPoint. So it should be table 10.1 for this. They do use stellar models, so our nice computers can really crunch numbers for us well. But solving these equations, we can make a mathematical model of the inside of a star and actually follow it through evolution as well. And so things like what we learned in the last chapter, diameter, luminosity, mass, the temperatures, the density. We learned some things about composition way back in chapter 5. So we can build a model and we can actually divide up our star into those layers, those concentric shells, those layers, and do these calculations for each layer as well. So 400 equations and putting temperature, density, mass, energy flow for each shell, and crank out these equations. And many of those equations I gave you last time on the board. But they can create a stellar model, so something about their radius, and then, so like this would be the interior of the star. There'd be 0 radius because you're right at the center. And if you went all the way to the outer part of this sun, let's say, it'd be radius of 1, right? So you're from internal going all the way out. So we could take a look at the radius. We could take a look at its temperature. I know you probably can't see these numbers, but at the center, it has 15.7, and this is in thousand, no, Kelvin, million Kelvin, so 15.7 million Kelvin, and the interior center of our star, okay, it's really, really hot, okay, and they're using the sun as an example. And then it gets cooler as you're going outward to the surface, okay. Density, so of course density out here would be the least, and then as you went towards the center, okay, your density would be the greatest. They're doing this with mass as well, so right at the center, 0, going all the way to the out. Solar mass, 1 for the whole thing. Luminosity, so they can do this for many of those properties that we talked about, crunching those numbers and create a stellar model that we could take a look at, and then they can go forward in time with it. And so here, for a stable temperature at the center, it's saying that it must be over 15 million Kelvin in order for the star to be stable. So if we learn something about what its radius is, what its mass is, we can predict then and use that model and extrapolate it to other stars and say, okay, well, if this mass of a star requires this internal temperature to keep it going, hydrostatic equilibrium and everything balanced, what would a more massive star's internal temperature have to be? Because it would have more layers to try to balance. And so they can figure out what the temperatures of stars are by running these models here. So high temperature, highly transparent, energy's flowing by radiation towards the center, so they can learn that. And then a little cooler out here, a convective zone. So lots of things they can learn by running the calculations and kind of taking it forward in time, like a time machine, to learn about the evolution of stars over billions of years. So how long can it live with the amount of mass that it has, and we're going to convert that mass into the energy, and how long can it live? So you could use that model to see how much fuel is getting used in your star and each shell, sort of thing, as it ages. And so that is what they have done in the 1960s, is when they kind of started looking at these stellar models and give us a lot of theoretical insight to the lives of stars. Okay, so nuclear fusion in the sun and the stars. So this is the means that a very dense cloud of dust and gas actually does become a star. Definition of a star is that it must be creating nuclear fusion within its interior. Okay, so igniting, they kind of call it, but it's really not that it's burning like we think of wood burning, but igniting, okay. What is going on in stars really isn't burning in the normal sense, but it's generation of energy, okay, powered by the nuclear reactions that are occurring in the center of the star, because that's where it's going to get hot enough for this nuclear fusion reactions to actually occur. So nuclear fusion is when that can occur. You get your temperatures high enough, pressures high enough, that nuclear fusion happens, and then you've got a star. That's your definition of a star, when nuclear fusion happens at the core. Okay. All right, so yeah, as it is creating that energy from the nuclear fusion, that's going to keep that interior very hot, okay, and it's going to allow for enough pressure, outward pressure as well. So these are going to get things moving very rapidly, your gaseous atoms, and so you're going to get collisions and forceful collisions. How they exactly yield energy, okay? The forces that hold the nuclei together. We've got these strong kind of nuclear forces inside the atom that's actually keeping the electrons and the protons together, okay? That they don't want to separate. Now, when you're trying to bring two atoms together, they tend to want to resist. Okay, remember those electrons are out there buzzing around that have a negative charge, and the negative energies don't want to attract one another. They want to repel. So the electrostatic sort of column barrier, this electromagnetic repulsive kind of a force, we've got to be able to overcome that column barrier, they call it. And so those collisions do have to be forceful enough, and you've got to get your molecules, your atoms moving fast enough. And that's going to take a very, very high temperature in order to do that. So the strong, okay, forces in the atomic nuclei are what we're trying to overcome. Okay. All right, so nuclear fusion. We're taking lighter nuclei and creating heavier nuclei. So the composition of our stars, mostly hydrogen and a little bit of helium in them. But the idea of nuclear fusion is taking the lighter hydrogen atoms and fusing them into the larger, the heavier helium atom. Okay, so we fuse the hydrogen nuclei into helium nuclei. Okay, and so in the hydrogen atom we have single protons, and in the helium nucleus we have 2 protons and 2 neutrons, and so you're producing a nucleus that is more tightly bound, okay, than the original hydrogen nuclei. And so when you do that, it's more tightly bound, that you don't need all that extra energy, and so that energy gets released in various manner of forms of energy being released. But this is showing that binding kind of energy as fusion reactions move down our diagram here. So we got hydrogen up here, lithium here, helium a little more tightly bound as you're going down our table here. It means that they release that binding energy of the nuclei and create a tightly bound nucleus. And so that energy is going to go somewhere. It's going to be released. And so we've got Einstein's equation of energy equals mass times the speed of light squared. And so you've got just this small amount. So we're taking a mass, right, the atoms, fusing them, okay, actually a more tightly bound atom, a helium atom. And so we've taken away a little bit of mass, right? And so that little bit of mass, it can't just disappear, it's actually converted into energy. And so that energy gets released during a nuclear fusion reaction, okay? So a little bit less. So making one helium releases a small amount of energy each time. Well, over millions and millions and millions of these reactions, that becomes a lot of energy over that. So significant amounts of energy are released in this manner, but the hydrogen fusion process in there. And so I mentioned how, you know, the nuclei carry those positive charges. They're going to want to repel. They're not going to want to go together. And so they have to overcome that column barrier. So that means those little atoms have to be moving just so rapidly to get those violent collisions. And so the gas has to be very hot for this to happen and move at those high speeds. And so once they do, though, there's a series of about 3 steps that happen, but in essence, you're taking 4 hydrogen atoms and making 1 helium atom, okay? Plus then all that extra energy that's being released during that process. So 1 helium, nucleus of the hydrogen, and creating 1 helium, okay? 4 hydrogen to 1 helium to get this. And there's kind of 2 ways to do it. This first one here is the proton-proton chain. It's sort of a series of 3 nuclear reactions by way of building one, at 1 helium. So you're taking the 4 hydrogen here, 1, 2, 3, 4, and going through a series of steps and creating the 1 helium atom out of that, okay? So a little bit of mass is gone, and then energy is released because of Einstein's equation. In the form, the energy can be in gamma rays, we call that. And here, this is neutrinos, which are basically neutral electrons, varieties of neutral electrons. Some other things, a little positron, which is a positively charged electron, another strange little subatomic particle in there. But energy's being released during this process. And this is known as the proton-proton chain. And temperatures need to be definitely above 10 million Kelvin. I keep seeing the K there, thinking 1,000. Kelvin is K. So 10 million Kelvin for this to be started. Okay, you need to get your temperatures in your core of your star above 10,000 Kelvin. And that stellar model that we had for our star, the sun, was 15.7 million Kelvin. So the sun does generate nuclear fusion, the hydrogen fusion in its core by the proton-proton chain process, okay? That's one way to do that. So they're just talking about what gets released as you go along, so kind of a 3-step series there. But a more efficient way, it's the same process though, it's 4 hydrogen making 1 helium. It is called the carbon, nitrogen, oxygen, or CNO cycle. This is the method that is used for much more massive stars than the sun. More massive in that they can get their core temperatures even greater. And so for this one, we need 16 million Kelvin in order for this one process to happen. And so upper main sequence stars, so those O and B stars that are much more massive, can get their cores hot enough for the CNO, or the carbon, nitrogen, oxygen cycle. So it's kind of using carbon as a catalyst, so it's a little more efficient process. But again, 16 million Kelvin for this one. It'll be dominating over the slower kind of proton-proton one. So they're taking you through that as well. And this one's just asking, well, okay, how do you support this theoretical explanation of how the sun sort of makes its energy? This other stars make energy. And so they got to looking for those neutrinos, that little particle that is part of the emission from these reactions. And so it was kind of showing you neutrinos from the sun's core, that little part that it talks about in here. So, and they have been able to detect some of these, and so that does give us some scientific basis of observations, way we can actually observe that this is happening. They began in 2000. That did confirm this. They would have been able to detect those neutrinos, and so, I mean, that's an amazing feat because these are nearly massless subatomic particles. So a little to support the theoretical side of things with actual observations. So, okay. That pressure temperature thermostat is very important in manufacturing your nuclear reactions, so the hydrogen fusion. So in order to do that, you've got to get that thermostat, your temperature, to be high enough. And so the inward, the more massive your star is, right, it's going to be collapsing down in. And that hydrostatic equilibrium that's creating the pressure because of your temperature getting higher and higher towards the center, right, it's going to create the outward pressure for this. And yeah, it's going to keep your reactions in control here, okay, because as that pressure builds, right, it's going to create an expansion in your star. As your star's expanding, well, it's going to cool down in the center there a little bit as it's expanding outward. So as it cools a little bit, well, gravity's going to take advantage of that and collapse it back inward, right? And that's going to, once again, heat up the center. And so you are getting sort of this back and forth, this pressure and temperature thermometer, kind of thermostat that's keeping things in balance, keeping it going, so that the pressure doesn't get so great and you blow your star apart, and gravity inward pull doesn't get so great that you collapse your star. So there is that balance between pressure and temperature and keeping things going, right? So yeah, if it produced too much energy, well, it's going to flow out the star, creating it to expand. That's going to cool the central temperature and its density, and it's going to slow down your nuclear reactions, right, until it begins to contract in. So it's not just a static kind of life for our stars that are on the main sequence. They are in this continuous inward collapse, outward pressure expansion, in that balance going on continuously to keep that thermostat from dying down, right, from becoming too cool. So in that nice balance between the gas and the pressure and the temperature is continuously happening within our stars. And looking at the HR diagram, if you recall the HR diagram, well, stars, our main sequence stars, remember the little slipper slide of the main sequence stars, 90% of your stars, okay, are spending their lives on the main sequence. And so the stars that are on the main sequence are generating their energy by nuclear fusion. They're doing normal star stuff, as I mentioned before. And these are the main sequence stars. 90% of their lives, they're going to be on the main sequence, and eventually they're going to evolve off of the main sequence, and a lot of that's going to have to do with what their beginning mass was. Mass luminosity relation, and so, you know, what their beginning mass was, sort of thing. Observations of temperature, luminosity, show that the main sequence stars obey this simple rule. They do follow the mass luminosity rule that we talked about in chapter 9, is that the more massive the star is, the more luminous the star is. Okay, so more massive. If you remember, luminosity had that little relationship. Let me find my... All right, you remember that little equation we had? One equation for luminosity, that, you know, whatever its mass is to the 3.5 power. So more massive stars definitely are more luminous, for sure. And that mass luminosity is kind of key to understanding our main sequence stars. So we got to consider both the law of hydrostatic equilibrium, which is the pressure balancing the weight that we talked about a little earlier, and the pressure temperature thermostat that we just sort of talked about there, that ends up regulating the nuclear reaction, so the energy production. A star that is more massive than the sun, okay, it has a much more weight pressing down on its interior. Yeah, its thermostat is set much higher, right? So its interior must have a very high pressure to balance all that extra weight on it. And so that means that its automatic kind of pressure temperature must keep up that gas interior being hot and very high, so to keep the pressure high. So that does have to be balanced. And a star that's less massive than the sun, so smaller than our sun, it has much less weight on its interior, so its little pressure temperature thermostat is set much lower. And so the massive stars are more luminous because they have to support that greater weight, right? Create more energy. And so our little ones don't have to, and so they're not quite so luminous. Okay. So yeah, the mass luminosity kind of relationship there. And it also shows you why, if you remember the end of the main sequence, why there is a minimum mass. Okay. 0.08 solar masses is that magic minimum mass, that lower mass on the main sequence, because if you're not massive enough, okay, you can't create that internal temperature, getting that up to 16 or 10 million Kelvin for the proton-proton chain in order to start nuclear fusion in your cores, in your centers. And so, you know, that's the definition of a star. So that's why we have sort of that minimum mass, that 0.08 solar masses, because they can't raise their central temperatures high enough to begin hydrogen fusion. Okay. Now we do have some objects that we do call brown dwarfs. So they're about 10 times the diameter of Earth, so they're pretty small, maybe about the size of Jupiter if you think of that. But they are not able to generate, you know, their own energy. They're very massive, they're still pretty warm because from their formation left over, but they cannot generate their own nuclear energy because they just haven't got enough mass to get their cores hot enough. And so the brown dwarfs fall in a gap between, if you remember the main sequence, and that we have the M classification stars. Those were like towards our red dwarf region. But so they kind of fall in between a gap of the low mass M stars and then massive planets like Jupiter. And planets never generate their own nuclear fusion. They don't generate their own energy. Planets don't. So the brown dwarfs are kind of falling in between that gap, and they've actually added a couple letters to the spectral classes in there with an L and a T to kind of represent some of these cooler objects. Brown dwarfs are what they're called. So they're not stars in essence, but they're very massive objects, but just not massive enough to generate their own nuclear fusion. So they may be pretty common in there. Okay, so yeah, on the main sequence, like I mentioned before, it's not an uneventful life. I mean, they are striking that balance between the inward pull of gravity and the outward push of the pressure, the internal pressure of that generation of nuclear fusion energy, right? So you've got this sort of balance that we have to get stable, right? And it has to continuously go back and forth like that. Gravity squeezing on the core and stars heating up and the outward pressure of that. So the core contracts, its temperature increases, and the nuclear reactions will run faster and faster for this, releasing more and more energy. So these gradual changes over time because, you know, a star is finite. It only has so much hydrogen that it can fuse to helium, right? It will slowly be turning that hydrogen into helium in its core. The core is going to contract and heat up, right? While the outer parts of the star become actually larger, that pressure, that outward pressure. So different layers in the star, different things happening within it. It will actually make it a little bit more luminous, and its surface will cool down a little bit. So if we think about our Hertzsprung-Russell diagram, it's going to move up a little bit and to the right. It's going to become a little bit more luminous and cool down just a little bit. So we'll look at that HR diagram. But yeah, during their lifetimes, they're going to, you know, just to be fluctuating a little bit around that main sequence. So here's our good Hertzsprung-Russell diagram. And so here's our main sequence, the little slip or slide starting in the upper left, going down to the lower right. And so it's sort of a zone in here, okay, that they'll kind of go up and to the right. They'll become a little more luminous, and then the outer surface will cool a little bit. So cooler end on this way, more luminous this way. So you'll see them kind of do this over time. And we can set up an idea of their ages just depending on where they happen to be on the main sequence, okay? And so gradual changes in their luminosity and the surface temperatures move them up and slightly to the right. And once, eventually they're going to exhaust their, internal hydrogen fusion happening. But it kind of lets us know how much hydrogen has been converted to helium in their cores. And so if our star is moving somewhere here, or the point that represents our star moves, like its luminosity increases or its temperature cools, right? We can estimate the age of the star when it's actually ready to evolve off of the main sequence and become one of various death throes. So it begins to die, basically. It's kind of done doing its normal main sequence kind of life thing. Now, when our star, the sun, they're talking about here, kind of undergoes these changes, the Earth will suffer because it's definitely going to become more luminous, but it's also going to be expanding. Its outer layers are going to be expanding. So it's only about 70% as luminous as it is now. So it's going to be continuing to get more luminous and more luminous as it continues, but it's sort of middle-aged right now. It's been burning, doing its thing on the main sequence for about 5 billion years now, and their estimate is that it's got another good 5 billion years to go for its mass and all that. It's a prediction, but yeah, life on Earth probably not going to survive when the sun finally does go through its evolution off of the main sequence and begins to go through its death throes. But we've got several billion years to, prepare for that. Maybe we'll find another place to live. I don't know. So life on the main sequence sort of thing. And so depending on their masses here, they will kind of estimate the approximate years that they would be on the main sequence. And this makes sense in that very massive stars, they have a lot of weight to try to balance. So that makes their interiors very hot, and they're going to consume their hydrogen fuel a lot more fast than say one of our little M low kind of down on the main sequence low mass stars would. Okay, so your spectral type O and B stars, right? Those are the very massive supergiants and giants, and they don't live very long. I mean, as far as star time goes. But say a 40 solar mass or a 15 solar mass, the O stars, so the very massive ones, only about 1 million years. And so that's not very long at all, considering astronomically. And then a B star here with a 15 solar mass, 11 million. I just mentioned that our star has already gone 5 billion with B years. And then, as you know, your masses are changing here. Here we've got one that's only a half solar mass, so half the mass of the sun. And this is 56 billion, okay, years. And so those red dwarfs, those ones that are the M spectral classes, those little red dwarfs, they can live for billions and billions of years. And it is said that every red dwarf that has ever been born is still alive. None of them have died. Because we're going to learn that the universe is only 14 billion years old. So if they can live 56 billion years old, none of them have died yet. And so those are thought to be the most common stars, those little red dwarfs, the low mass in ones, because they don't have so much mass and pressure to try to balance. So they just slowly go through their fuel and can live on for billions and billions of years. So the higher mass ones live the shorter lives because they're gonna go through that fuel a lot more rapidly. And so looking at the birth of stars, the key to kind of understanding star formation is relating it to very young stars, these hot O and B, very bright, luminous, and hot stars, and sort of the dust and gas around them and between them. So the interstellar clouds of gas and dust. So space isn't just empty void. There's a lot of gas and dust in there. And being around these young stars, that actually ignites, sort of propels and perpetuates star formation. And so stars, as we could suspect, would come from these such sort of interstellar medium clouds, they call them. So the interstellar medium, low density gas and dust. And this, they're looking at the Orion, kind of Great Orion Nebula in Orion, the constellation Orion, as sort of a nursery place for new star formation. They have some very bright stars, young, bright stars, very massive stars there that can ignite further star formation. So very microscopic, the interstellar dust in there. And then they're talking about, well, how do we even know there's interstellar medium? They do take a look at it, 3 different kinds of nebula that they present to us here on how we could see, very hot stars can excite that, and then you can see the dust around it. The starlight can reflect off of some of that dust as well, okay? So you can see it from that way. And sometimes we can see it silhouetted with a sort of dark background region. So a bright nebula, they call it. So it's a variety of nebula that we can study that we do detect then the interstellar medium. Okay, and they're just talking about different ways here that they look for that. Okay, but our main thing we want to look at here is, and they look at it with X-ray and infrared radiation, is that how can we get this sort of diffuse, low density cloud of dust and gas to collapse? And they're saying in here that it won't ordinarily just want to collapse on its own. Over time those clouds can get pretty dense, and so it would be in those most dense molecular clouds, we call them dense molecular clouds, that we would have any hope of getting enough kind of collapsing or gravitational pull to create any sort of condensing to happen. And so it won't just ordinarily happen on its own, but you can get the pull of gravity kind of making these extra dense molecular clouds, they call them. So that gravitational energy is getting translated into or converted into thermal energy. So that can start to heat things up. So we're converting gravitational energy into thermal energy. But that alone isn't quite enough. We need some sort of shock wave, something to really cause a collapse of our dense molecular clouds. So they're pretty much going to resist that. But you can get some very dense regions, as I mentioned, these dense molecular clouds. This is where our stars are going to be born. But we need some things that are happening in here, in these densest parts. So gravity alone's not quite enough, okay, not to really get them to collapse into stars. We need a shock wave, as they're talking about here, the astronomical equivalent of a sonic boom kind of thing, to compress and disrupt these into fragments. So a shock wave approaching interstellar gas cloud, right? It compresses it and then become gravitationally unstable, okay? And some regions in there kind of fragment it a little bit, okay? And then enough to, you know, really start to collapse and get hot enough in the centers. Got to be at least 10 million Kelvin before we can get nuclear fusion to happen, hydrogen into helium, right? 4 hydrogen into 1 helium. The definition of a star. So some things they talk about on what could create that shock wave. The first one here is a supernova explosion. So supernovas, as we'll learn in chapter 11, are deaths of stars. I mean, these cataclysmic explosions of stars. So supernova explosions would certainly be enough of a shock wave. So that could be one way that would compress the interstellar medium. Another one is in the birth of very hot stars. So near our O and B stars. We know that the O and the B stars are going to be young. They're very massive. They probably haven't moved very far from their birthplace, okay? And so that's a great place for more star formation to happen, because as that new star is like bursting forth, okay, producing all that energy, these young, very hot stars, that's enough of a shock wave. The birth of very hot stars, they're so luminous that it emits a tremendous amount of ultraviolet photons, which can create a shock wave and even spur on more star formation. So a death of star, supernova explosion, and the birth of these very hot O and B stars can create star formation as well. And they, I think, mention a couple other things. Collision of 2 interstellar clouds. So that could create a density enough that could create a shock wave. Another one that when we get to our galaxies we'll learn about star formation in something like the Milky Way galaxy, but these spiral arms, the beautiful spiral arms of our galaxies that are spiral, and the Milky Way galaxy is, that can interact with one another. And so trigger formation, or star formation, can be triggered in those spiral arms themselves of a galaxy. So a variety of ways, but in some way we are getting the collapse of an interstellar mass, okay, very dense kind of molecular cloud, and that's where these stars are born then. And certainly gravity is that force. Gravity always wins, right? Gravity would be the force that would instigate the collapsing of the cloud. So once it does begin, star formation is going to spread like a grass fire, basically, triggering the formation of more stars, which will also be very massive, and then triggering more star formation. So we do kind of get clusters of stars we call star clusters, and they're held together by their combined kind of gravity. Or you can get some things that are called stellar associations. They're not really gravitationally bound to one another, and so they can move and drift away after, you know, several million years. They can kind of drift away from one another. But the youngest associations, of course, are rich in these young stars, including the O and the B stars. And so those lifetimes are so short for an O and B star, if you remember that. A million years here, a B star, 11 million years short. Astronomically speaking, that's short. So that we know that they aren't probably very far, haven't drifted very far from their birthplace. So these young stars are like signposts of their birthplace. They haven't gone very far, so they're located very close to where they were born. So sort of like a signpost, a brilliant signpost of where they actually formed, okay? So once that part of that cloud is triggered to collapse, gravity is going to draw the atoms toward one another. Gravity is going to win, and it's going to just initially fall. Those atoms are going to fall unopposed, okay, until you get enough that inward velocity of the atoms are going to get converted into thermal energy. And so that temperature is going to continue to rise and rise. And when you get to 10 million Kelvin, right, our little pressure begins to form. So it's not just collapsing anymore. We're starting to get the outward pressure balance. We're going to call that a little baby star or a proto-star, okay? And so this is destined to become a star. Once it gets that temperature, 10 million Kelvin, we're starting that nuclear fusion in earnest, that gravitational energy into thermal, right? And then definitely internal temperature high enough, nuclear fusion's taken over, and it has graduated toward the main sequence. It has become a stable star doing the hydrostatic equilibrium, the pressure temperature thermostat, and it's on its way to the main sequence. It's going to spend 90% of its life on the main sequence. So these little baby stars, protostars, okay. And they're just kind of taking a look at how long it might take some of these to reach that main sequence, right? And a lot of that has to do with what their masses are. Something like the sun took 30 million years to reach the main sequence. Something like a 15 solar mass, well, only about 160,000 years. So those very massive stars, because they're balancing all that extra weight, they're going to get their internal temperature, to increase much more rapidly than a lower mass star is. And so those don't take quite so long to make it onto the main sequence sort of thing. And so, yeah, this is like a 15 solar mass here. It only took it, 10 million years. 3 solar mass took it 640 million years, So varying masses are going to depend on how long it actually takes that star to make it to the main sequence, get its temperatures just right so we get the nuclear fusion to happen. So again, those stellar models are what we're using to kind of help us understand this. Okay. So our little protostar stage is less than 0.1% of your star's total lifetime in there. And then this was just some evidence that we can be sure that star formation is going on right now. And so again, the Great Nebula of Orion is sort of this nursery place for stars to be born. They're finding some things called Bach globules, very dense zones of gas and dust in there. So very first stages of star formation. Her big Haro objects, little jets coming out, flickering nebula. So again, little birthplaces for these with lots of gas and dust around them. T-Tauri stars, protostars with about the mass of the sun. So rapidly rotating stars, little dynamos going on. So we know these are active places for a star. So now we know how to make a star. All we need is some way to compress a greater than 0.08 solar masses, right? Because other than that, it's not going to be able to get hot enough to produce the nuclear fusion. But something more than that 0.08 solar masses, that's the low end, right, of the main sequence of interstellar materials, so it's really dense molecular cloud in there, into enough region of space, and gravity is going to do the rest of the job. Gravity is going to win, right? So that's the force that's sort of driving the formation of our stars. It's responsible for the collapse of that interstellar medium. And these are just some gorgeous pictures of the Orion Nebula, kind of showing the sort of interstellar kind of medium in there. Very bright stars. There's some really young, bright O and B stars in Orion that they're talking about, and their various ages, millions of years here and there. So just some nice, beautiful pictures that they shared with us of evidence of young stars. And so that's pretty much chapter 10. So we got our stars birthed. We understand what it takes to create the stars and what it is that's going on in the internal structures of the stars. So nuclear fusion, that there are these concentric shells and layers within our stars, that different things can be happening in those layers, as we'll really see that in chapter 11 when we are off the main sequence. We're going to have different things happening in those layers that are going to lead to various death throes. So we've got our stars born, we kind of showing you what they're doing as they're living on the main sequence, and chapter 11 will be devoted then to we're going to go ahead and kill our stars, so the deaths of stars. And so make sure you look at all your bullets on your study guide and that you have some good information for that. And if you have any questions, make sure that you get with me on that, and I'll